Just the head.
Just decapitate this bear.
No,
It's already dead.
I can tell you from experience that decaying and liquefying brains is one of the most smelliest, second only to the digestive system. As brains liquefy, they give off this super toxic smell, and they can, in fact, be incredibly dangerous because decaying, this is where zombie apocalypse, it's not just the zombie bite that will kill you. As the zombie brains are liquefying, what happens is they get, it's not a bacteria and it's not a virus, it's something called a prion. And it is in between a bacteria and a virus, but it is, our brains are very susceptible to prions.
Why you shouldn't eat human flesh.
That is exactly why you don't eat human flesh, because you will end up with prion encephalitis and you'll die.
Doesn't that happen with sheep brain or something like that?
It really can happen with any brain, is that they can develop, and that's why eating brains is kind of a gamble, because you can end up ingesting these prions, which will infiltrate your brain and kill you. So don't eat brains unless you're a zombie,
And don't
and
eat
then
people.
you don't have to care because you're already dead. We come up with the craziest opening conversations, you guys. I love it. I love it. And I love that your very first go-to this morning was penis. And yes,
A whole tangent.
It sure did.
I
Went from penis to dead deer.
woke everybody up with the penis and the dead deer. And yes, I have two
Penises are deer.
cat penises. I have one deer and two penises and two pairs of testicles and two tarantulas
And armadillo.
and one armadillo in a pear tree. Oh, that's
Oh,
funny.
yeah, true.
And what? And my mortician kit, which is really, really uncommon. That's what kind of my prized possession.
I thought
because-
of your mortician kit this weekend when I saw the picture of Prince Philip floating around Twitter.
Oh, geez.
He looks like a corpse.
What is wrong with
does.
He's
him?
old.
He's
Like, I know he's old, but
170
like-
years old.
No, but my grandmother's 80 and she does not look like that.
No, he's like, no, but seriously, he's like 98, 99 years
She-
old.
He looks
How
really
is the
sick.
queen still alive?
Yeah, your body as it ages,
Money.
it's decaying on you.
Crazy.
Oh my goodness. I just
Crazy.
died.
Although I also find it kind of,
I'd rather die.
I have now officially infiltrated all of your brains. I am living rent-free right here.
Evicted.
Living rent-free right there. You can't evict me once I'm in. I'm like mold. Can't get rid of me.
You're there.
I'm there forever. All right, so let's do a wee bit of review. We started talking about our organelles yesterday. Here we have the mitochondria. Do it once with enthusiasm for me.
Powerhouse.
Of the cell.
Okay.
Cell.
I said enthusiastic.
Cell.
You're rude. That was not enthusiastic. The rest of you, marginal job. We talked yesterday that the site of the mitochondria is where cellular respiration takes place. That's where our active gas exchange is taking place. And it's taking place here in these folds, which is also the area that we have the formation of ATP, which is called the cristae. We talked about all that yesterday. Here we have where our mitochondria can replicate through fission. It's not like you have a mommy mitochondria and daddy mitochondria having, a little family. These just pinch themselves off and form two. And so in our cells that need more energy, we are going to see a higher number of mitochondria. That makes sense. If you need more energy, then you would need more of the thing that produces the energy. Here we just had our little picture that we looked at. The shape is elliptical. And again, we have these cristae, which are these little folds, they almost look like little brain folds. And this is where the primary site of ATP. Someone remind me what ATP stands for. Very nice. Adenosine triphosphate, and then we break one off, and we have ADP, and that's by breaking that bond that releases the energy. It's in my eye today. My eyes have gotten lower on my face. Ribosomes, these are the most abundant organelle. We have fixed ribosomes. Tell me the part of the cell where our ribosomes are fixed to. The ER. In fact, the rough endoplasmic reticulum. And it is called rough because it looks like it has little bumps on it because those are the ribosomes. But ribosomes can also just be free and just be floating around the cell. This is the part of the cell that produces proteins. We've talked about this at length, how we have our tRNA becoming mRNA, and then we have rRNA that feeds through the ribosome spits out the protein. There's our endoplasmic reticulum. It is a continuation of our nucleus, which is nice because our messenger RNA doesn't have far to go to find one. So this is where we left off, and this is where I'll start recording. Get this up. I know I'm a little behind. Oh, I'm already recording. Hey, go me.
Go Doug.
Go Doug. Doug is on the wheel, and I didn't even know it. Sometimes he gets on the wheel, and I'm not even aware of it. So this is where we ended yesterday. We were talking about the smooth endoplasmic reticulum and how it works and functions similar to your organs that detoxify you. We talked a little bit about things that can cause a cellular change, and technically a subcellular change, like alcohol, different medications. This is why you may be taking a medication, and then you go get your levels checked, and the doctor's like, well, we got to give you more because we have increased the amount of our smooth endoplasmic reticulum. If you are a raging alcoholic, you have some people where half of a beverage and they're, snoozing under the table. And then you watch, what is that one show?
Shameless.
No.
Intervention.
Yeah. See,
Intervention.
you are in my head. You are in there. We have psychic connection today. Intervention. That show is insane. Where they're like, hey, yeah, I only drink like a liter of vodka a day. And I'm like, what? Oh my goodness, that would kill me. So there's just another picture for you little visual learners. Here's my nucleus, there's my rough endoplasmic reticulum, and there's my smooth endoplasmic reticulum.
Would you mind going over cisternae?
Absolutely. So the cisternae, this is where, so in our endoplasmic reticulum, where we have the ribosomes, the cisternae, this is where, so we've spit out, the ribosome has spit out the protein. And that protein has to be modified before we can send it to the FedEx store. And so the cisternae is what we are using to modify and package that protein for transport to the Golgi, which we're going to talk about next. So once we spit the protein out of the top of the head, the cisternae is the one that gets it ready to send to the UPS store. So then we have our Golgi apparatus. This is our shipping, UPS, USPS, FedEx, what have you, whatever shop you want to compare it to. And this is the area that receives the proteins that are composed of this repackaging called the cisternae. Once we have created and repackaged the proteins for transport to the Golgi, that's when we refer to them as cisternae. So the Golgi gets the cisternae, these repackaged, remodified proteins, and the Golgi is what decides and how it ships Do we need to send this somewhere else inside the cell, or do we need to send this out of the cell to be beneficial to the body somewhere else? So the Golgi really does act like our UPS store. They get the package, they look and find out where do we need to ship it, they put the little shipping label on, they put it on the right truck, and they get it to the right place. That's it. That's all Golgi does. He's just shipping, just USPS. It is USPS, United States Postal Service. Yeah, USPS or FedEx, whatever. And so he just simply remodifies the protein, repackages the protein, and makes sure that that new protein is sent to the area that it needs to go. The other thing that Golgi can do other than just shipping is he does have one creation capability. And he is able to take sugars and bind them together. What does the prefix poly mean? Many. So a polysaccharide is many sugars bonded together. In fact, the literal definition, if you want nutritional definition, a polysaccharide is any molecule that has more than two. Because if I have a single molecule sugar, what would that be called? A monosaccharide. And then if I have a double disaccharide, and then anything greater than two, poly. Could be 3, could be 12. Poly is just referring to more than 2. And this is one of the many areas where we are able to assemble those bonds and create these complex sugars. And that's it. Are you guys still doing your terriers? No, hounds.
Hounds.
Hounds. There's a lot of hound dogs. I used to have a dog that was half lab, half greyhound. Oh. Yeah, he was the weirdest looking dog ever. He had the big, heavy body of a lab, but the super graceful head and legs of a greyhound. So he was this super leggy, but kind of heavy, chunky. Oh, he was the weirdest looking dog ever.
Tomato on toothpick.
He did what?
He was a tomato on toothpick.
He did. Now he did thin out when he got older and had a little bit more of a slender, more greyhound-like body. But yeah, he was a weird looking dog. The best dog I ever had. He was amazing. Well, second best dog I ever had. He was amazing. His name was Jerry. I know. I had Jerry and Julie. So here we have a picture. Let me get my pointer here. So here's what's going on. Here's what we know so far. We've now had our RNA come out. We have bippity boppity boop, created a protein. That protein is packaged as a cisternae. We transport it here to the Golgi, where it gets unpackaged and assessed. The Golgi apparatus has now decided this particular protein needs to go to the outside of the cell. So what it does is it encapsulates it in this little transport vehicle, essentially no different than putting it on the back of a truck. And this little truck now runs and goes, and then it joins with our phospholipid bilayer and releases the proteins outside without compromising that cell membrane. Does that make sense to everybody? I love this picture because it really does kind of dynamically show exactly what's happening.
Is that when it makes a little cake?
So here is where you are making the thing. You put it in your car after you've put it in the shipping box. You drive the shipment to the FedEx store. The FedEx store looks at it and says, okay, here is the appropriate shipping label, and here is the truck that we need to put it on. The truck then drives it to the outer barrier. Now we can't drive the truck through the cell membrane for why? Because it'll rupture and kill the cell. So what it does is it binds with it and then releases And now these proteins would be scooped and picked up from other things outside of the cell and further transported.
Is that when it meets the phospholipids?
So in here though right here, this is the cell membrane. This is the phospholipid bilayer. And so this transport vehicle is also made of phospholipids so that it's very easily able to join up. And then what happens is it just becomes part of the cell membrane.
It just joins.
It just joins and becomes part of it. And then these are released. And then there's another guy we're not going to talk about, but there's another little guy waiting out here to scoop them up and take them wherever it is they need to go.
So if the protein is released within the cell, does it need this little capsule thing?
Yeah, so what would happen is we would have a separate capsule that would then transport it to wherever it needed to go. So if it needed to go to another organelle, it would then, the organelle kind of joins up with the transport vesicle. It would release the proteins into the organelle, and then those two would detach. They would not become part of the organelle. They would simply detach. I think in my brain, although sometimes my brain does not work the same as everyone else's brain, I think of it like an airplane in the sky that needs gasoline, and you have one plane come up over and then join up, fill it up, and then detach. So the plane that needs gas is the thing that needs the protein. You have the little transport vesicle come over, deliver the protein, and then go away. I don't know if that analogy works.
So if the Golgi apparatus is like the shipping, like the FedEx store, does it itself need protein, like when it needs it, instead of just transferring it?
Yeah, so if it needs a certain protein or it needs something, it would just ask for it and then it gets
It
delivered.
just wouldn't leave.
It just would never leave. All right, so let me get this so that we can see what was happening here. Lysosomes, these are kind of interesting. So what lysosomes are, these are also formed in the Golgi. Now this is not a delivery system for proteins. This is a delivery system for toxic acid. Obviously, am I simplifying it to the millionth degree? Of course I am. But think of these lysosomes similar to containing a digestive enzyme, something that can break down very easily and quickly other things. So these lysosomes, we refer to them as the stomach of the cell. So one of the things that lysosome does, let's say I've got a foreign invader, and I happen to be one of the inclusions, one of the voids, and I'm like, hey, here's a foreign invader right here. And what I do is I go, whoa, whoa, and I get the foreign invader, and he's now trapped inside me as an inclusion. But he's just like, I don't want to be in here. So the lysosome will come over and bind with me and deliver digestive acid that then would be like, and kill this and dissolve it and save the cell. And then he would disengage and go on his way. So he really is, he's kind of the digestive stomach of the cell. Although the big difference obviously is, even though we call him the stomach, we're not using the stuff he breaks down as nutrition. He's just breaking down things that are not supposed to be there.
So is that kind of like the lysosome story? It breaks down all the germs and the particles?
So to lyse, the medical term lyse or lysis means to break down. We just had a light bulb moment. So to lyse something, like if I had this is what's happening here. I'm going to use a lot of med term. Are you ready?
No.
Yes, you are. Cellular autolysis. Autolysis, self-breakdown. What ends up happening here, because lysis means to break down, as this cell gets older and older, cells don't live forever, just like we don't live forever. We have an expiration date, so do our cells. So, but what programs the cell to be taken out of circulation. As they get older, they have more and more and more of these lysosomes, lice to break down, the function to break down, lysosome. And so what happens is as the cell ages, they get more and more and more and more and more of these. And then when the expiration date of the cell has been reached, all of the lysosomes are just like a time bomb, and they all open at once and just release that digestive enzyme into the cell, and it just breaks down the entire cell. The cell is then killed. Anything that can be recycled is reused, and any parts that can't be reused are discarded. So that's why we also kind of refer to this, although trigger alert, we do call this the suicide component of the cell, because it does self-destroy the cell.
So it protects the cell and also destroys it.
Yep, it protects the cell by having destructive properties. But then ultimately those destructive properties are what ultimately destroy the cell. And this is where another case of an autoimmune. There are conditions where your body prematurely creates these additional lysosomes. And before the cell is ready to go, before the expiration date, for some reason, the lysosomes have just gone rogue and they're destroying all of the cells from the inside.
Can that happen during pregnancy?
Yes and no. During pregnancy, it is not so much the lysosome, but the immune system military attacking the fetus. And there's a million different reasons why that could happen. The most common, of course, being that the baby has a different Rh blood factor than the mother. Because if the mother is one blood type and the baby is another blood type, the immune system says stranger danger, kill, kill, kill. Not so much a lysosome issue though. Oh, let me, that they just simply increase in number as the cell ages. So it's protective and it's destructive. I find that fascinating.
It's like a double-edged sword.
It really is. The thing that is protecting the cell is also the thing that will ultimately destroy the cell.
Like humans on Earth. Well, I mean, think about it. We protect the Earth, but we also destroy it.
Very true. We could be considered the lysosomes of the earth, causing the ultimate destruction of the death of the earth. That's a little grander of a scale than I was going, but okay. So this is the action. This is what I'm talking about. Again, this is just for you little visual learners so that you've seen it. So here I have something that has an inclusion that has a little collection of foreign invaders. I don't know what these are. I'm going to call them foreign invaders. Our lysosome binds and releases the digestive enzymes. And then what happens is this vesicle, actually these are the enzymes, my apologies. This is the foreign invader. We release it, and then what happens is we break it down. So here's my bad guy. For some reason, it is trying to enter my cell, and the cell is like, no, you can't come in. You're going to jail. And it wraps it into this little jail cell, which is called the vesicle. And that's when our lysosome comes, spits out his acid, and breaks down the bad guy. So this is on the case of something coming into the cell that should not be there. And that's it. And he just does that over and over and over. And then after he has released his digestive enzymes, we just get another one to replace him and another one to replace him until we have created too many and they ultimately kill the cell. Any questions? What questions can I answer for you further about our lysosome?
What did you call the little capsule? What's the difference
It's a-
between the bowl and like the little caves? Isn't that the same thing?
So yes and no. It really, if we want to just simplify it to where we are, the terminology, I got termination on the brain now. The terminology really is dependent on what is it carrying. So in this case, a vesicle is also an inclusion, which is just a catch-all term for something that is encapsulated. When we talk about our calveolae, when we talk about our cisternae, those are referring to inclusions, vesicles that are carrying specific things. Does that make sense? Okay.
Why did
Now
you
it does.
let anything in the first place?
So that's a fabulous question. And my answer is, the problem is that there are some things that are either small enough to pass between the molecules. Because remember, this is not a solid wall. There are little spaces in between our phospholipids. They can pass between the phospholipids. We have other things that can fool. They have a fake scalped ticket to the show. They're allowed into the stadium and are immediately caught having a fake ticket. So if we're going to continue with the idea that we have the pores general admission, we have our selective channels VIP, but ultimately they both get you into the stadium to watch the show. Some of these little guys are pretty tricky tricksters, and they've got a photocopied ticket, but gets them in, but they get caught almost immediately. And then we have others that gets them in and they never get caught. Like we talked yesterday about malaria, which is a blood parasite that just hides. And the inside of the cell, because we don't have that glycocalyx, doesn't recognize it as a problem. And he just lives and proliferates inside the cell until he takes over your body and kills you. I find that fascinating. It's something a billionth of our size can kill you before you even know you've got it.
So it can go through the cholesterol?
Oh, just one sec, I got a hand right
About
beside me.
malaria, so sickle cell anemia, something that's super common in Africa, is caused by two genes that are non-dominant. If you have one of those genes, you are resistant to malaria.
Yes, although sickle cell anemia in itself will kill you.
Yes, if you have both.
If you have both,
Genes.
because we've all heard the term sickle cell. So, and it's called that because it looks like a sickle, looks like the knife axe thing that death carries. It's called a sickle. Well, what a sickle is, this is actually kind of fascinating. We're getting off of this a little bit, but we are still talking about cellular morphology, or the study of shapes is morphology. What a sickle cell is an abnormality in your red blood cells. There's specific, again, don't write this down, it's just so you've heard it before, and I happen to know a wee bit about this. Something called a drepanocyte. And what a drepanocyte is an abnormal red blood cell. And what happens is your immune system's job is to get rid of what? Abnormal things. And it starts breaking down these sickle cells. The problem is that the majority of your cells are being created as sickle cells, as drepanocytes. The problem is the more red blood cells you kill, the more red blood cells you create, and therefore you may have started with just a small number of drepanocytes and have now waterfall cascaded into mass production. And now your body is in full assault mode. And when your body goes into panic, holy crap mode, we start getting friendly fire. And now we're just taking out drepanocytes and healthy cells and healthy tissue. We're just like blitzkrieg the whole darn thing, get rid of everybody, and then you die.
The idea behind the resistance to malaria is that one copy of the gene rather than just two just modifies the shapes of your cells enough that the malaria can't hide.
Right, but does not modify it to the point where your
where it's
body
not
is
there.
recognizing it as an abnormal. Genetics and cellular morphology is so fascinating. I love that you love this. I get excited.
Okay, so I have something similar to that. I have a blood disorder called severe psychosis. It's something like that. And it's, well, what they told me is that it's similar to sickle cell. Is that what you said was?
Sickle
Okay.
cell. Uh-huh.
And what it is like, I guess my blood cells are like donut holes and they die a lot faster So my body's constantly making them, but in the day, my body kills 10,000 of them in
Right.
a day, whether y'all would only kill like
Sure
100.
thing. So there are in fact though many red blood cell morphology disorders. Anything that causes your immune system to look at something and say, stranger danger, that is a disorder. And there are hundreds of conditions that can cause red blood cell disorder. In fact, a lot of the red blood cell disorders are named after the shape that the red blood cell takes. And you're going to learn about these too. You have the drepanocyte I just talked about. You have dicryocytes, acanthocytes, echinocytes. You have Howell Jolly bodies. That one's fun to say. It sounds so happy until you realize it's going to kill you. You have Heinz bodies, which can be from onion toxicity, acetaminophen toxicity. So anything that causes an abnormality in the red blood cell can target your immunity group to say kill, kill, kill. I know, right? Come on,
Wow.
guys, this is exciting stuff. Do I
So
have?
with the phospholipids, you know, it can get through, does it go through the cholesterol? Because I know the cholesterol is wedged in between.
So the cholesterol is not wedged between every single one, though.
Oh, okay.
Think of it like a fence. You have your fence post, fence, 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 fence post, fence, 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 fence. Those fence posts are the cholesterol. Because remember, the cholesterol is there primarily to maintain the strength and integrity of the cell membrane. So if they were wedged in between every single one, then yes, we would have a cell that was protected, but a cell that could not move and morph and change its shape.
From my understanding, the rafts on the phospholipid bilayer have more cholesterol, which makes them hard so they can like separate and allow things in and out.
So they're like the
Yes.
intermediate fibers, right?
But on the outside.
On the outside.
So would you say the lysosomes are the ones in charge of like autoimmune diseases?
No, so they are in charge of just cellular destruction, and it is your immune system that ultimately will tell it to go into kill, kill, kill mode. And so I keep waving up here, and I know you guys are like, oh my God, is there a bug? What is happening? So I am probably one of the most visual people. I just see my world differently than most. And in my mind, I have this, whatever deity you want to talk about. I call it immunity Groot. If you want to call it an immunity God, an immunity Thor, whatever. It is this invisible thing. This is my immune system in this cloud right above me, looking down into my body, into every little cellular crevice, monitoring for stranger danger. And then I have the patrol units that are reporting back to immunity Groot. I have little beacons I can set to direct a response. Lysosomes just happen to be a small component of that ultimate immunity protection.
So our cells are pretty much like killing themselves all the time
Yes.
without us even knowing. Like if we're sick, like before we even get sick, then like
Yes.
we could have it and it's just dead and we don't even
And
know.
in fact, so when you get sick, and this is another thing I find fascinating, if you get sick, okay, and initially you get this, we've all felt it coming on, right? You wake up in the morning and you have the little bit of a thick throat, and you're like, oh geez,
It got
this is bad. It got me. You're like, I'm hit.
It got me.
Well, it's not the bacteria or the virus that causes your symptoms. It is your body's reaction to it that causes your symptoms. The fever and the mucus and the cough and the shivers and the shakes and the headache and the muscle aches, all of that is residual from this massive war now going on. Think like the first 5 minutes of Saving Private Ryan happening inside your body. And it's very dramatic, and it is that is giving you the symptoms of the illness.
Why would you have a headache though?
Well, you have a headache because your body has risen the temperature. And when your body is fight, 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 kill, 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 all of the energy that you have, because you have a finite amount of energy, every cell in your body, super greedy. Everyone gets paid. Well, the problem is now is the cells who are in the war are demanding more payment, which means that the cells you would use for normal everyday things like, oh, I don't know, digestion, are not getting paid. And the problem is that if you're using a ton of energy, but not taking in any energy, now you're having to use even more energy to break down energy to provide energy. You're not taking in drink, you're not taking in food. What happens if you don't drink and you are sweating out a ton?
Dehydration.
What happens to you when you get dehydrated? Bam. See how I
Got it.
connected all that
Yes.
together?
It-
That is the critical thinking train, where you go from, okay, this is what's happening, this is the outcome, how did I get here? That's what I love about veterinary medicine. I just had, in fact, it's kind of exciting. I just had a major, I'm taking a class called Emergency and Critical Care. And we're on, this week's chapter was all about neurological disorders. So like idiopathic seizure disorders, you have trauma, spinal cord trauma, all of the things. Vestibular disease, oh my God, what is it? Not GDV.
Come on, Doug.
It's the one with the dachshund. Anyway, I'll think of it later. Anyway, it's a spine injury. So here, just to give you an idea. Thank you. IBD. And so a whole chapter. So I had a big test on it yesterday. Here, this will put things in perspective for you. My test last night was 5 questions.
When they fill in the, like, write out.
Long
You
answer.
had to write out, you're right.
It was a 5-question test and we had 60 minutes to do it.
Oh, Lord.
And I nearly ran out of time. Yeah,
Huh.
so welcome to my world.
Don't do that to us.
Oh, I would never do that to you. But one of them, the first question was, explain the difference between generalized and focalized seizures using no less than 250 words.
That's an essay.
That was one question. All right, so here we have our inclusions. And I've used this word over and over, and inclusion is just a space in the cell. And we've got a lot of different vocabulary to describe these spaces. We have our transport spaces. Here we have something called a vacuole, which is just a larger space. Vacuoles tend to be kind of the jail that we just talked about. Janet,
No, you didn't.
did I miss one?
Yes.
You were on.
Look at that.
We were just talking.
I was just chatting and I was like, man, let's just chat through this one. Because this one's important. Thank you for bringing me back. Peroxisomes. Peroxide. Sounds like what?
Hydroxide.
Hydrogen peroxide. Guess why this is called a peroxisome? Because it is using hydrogen peroxide. How fun is that? So here's what happens. These peroxisomes, now remember, all cells have some or all of these organelles. Peroxisomes are very common in our liver and our kidney cells. Areas where we need to detoxify things. What happens is we have these little enzymes. All right, let me back up for a second. So when are you having cellular damage being done to you?
All the time.
All of the time. All of the time. Right now you have cellular damage being done. And when your cells are damaged, they release this thing called a free radical. And free radicals are evil. Free radicals are not nice guys, and their whole job is to run around and create more damage. We have a bunch of different ways that we can prevent that damage from continuing. This is one of them. So this peroxisome, because you got to imagine, if let's take just my kidneys, for example. My kidneys' primary job is to retain stuff that I need and get rid of stuff that I don't. Well, because they're dealing with the danger, right? They're detoxifying. You can imagine just how much more cellular damage they would have than any other random everyday cell. Free radicals are going to be a humongous problem. What the peroxisome does is it converts these free radicals. This is the enzyme it uses. It's called a peroxidase. Converts them into hydrogen peroxide. Well, do I want hydrogen peroxide circulating around in my body? Of course I do not. So I have a second step called a catalase. Cata meaning break down. And it breaks that hydrogen peroxide into water, which is something I can use. So the peroxisome has these two enzymes, it's a two-step process. It takes the peroxidase, which converts the free radical, stops it from being damaging, and converts it into hydrogen peroxide. And then step 2 is our catalase, where we break that hydrogen peroxide down into something beneficial that we can use, which is water. So
it turns from something that could kill us to something that we can use.
bam! Yes,
Wow.
I know. I know. Very cool. So it is. It's taking something that ultimately would cause so much cellular damage that it would kill you. And it is converting it into something that our bodies desperately need and hold on to like a crazy person. Because we are water carbon-based beings. 60 to 70% of our physical makeup is water. Almost everything about our anatomy and physiology is set up to hang on to water. This is just one of those steps where we can convert something into water.
Is that why there's more murders and crimes on full moons?
No,
Because I mean we're water babies.
we are water-based. That is more of a psyche versus anatomical. But that is not so much the murders, but yeah, if you ever work in emergency practice, God help you if you're working on a full moon.
My mom's a labor and delivery RN.
Oh, Lord help her. Groot help her. Groot help her. All right, so here we have our inclusions. Again, they're just voids, depending on what they're carrying, what they're doing. That's how we name them. We have our vesicles, which, for example, are our transport vesicles, just moving stuff around. We have something called a vacuole, which is just bigger. This is the thing that predominantly traps stranger danger. All of these, though, if I say it's an inclusion, it just means it's a void. It is something, a space to do a different job.
So it's kind of like the actual space where it's a vacuole and like everything's kind of like.
Yeah, so there's a white blood cell that uses vacuoles. He's my favorite white blood cell. Of course, I have a favorite. His name is monocyte. And when he's in the bloodstream, he's just this mild-mannered, top of the morning to you. I don't know why he's English. Has a top hat, but he's top of the morning to you. But he's like Brent Banner. Because when the immunity group goes, oh no, stranger danger in the tissue, monocyte, smash. And monocyte migrates out of the blood and into the tissue and turns into the Hulk. He turns into something called a macrophage, which quite literally translates into big eater. And he has these giant vacuoles that he goes and he's like, and he's just absorbing all of the stranger danger and trapping them in the vacuoles.
Is that where the lysosome is?
And then he would have the enzymes to either kill the thing or he sacrifices his life for you. So whenever you think you're alone and no one loves you, just know you have an entire battalion of cells that are quite literally going to sacrifice themselves for you. Because in the death of the cell brings the death of the foreign invader. So, but yeah, so that would be an example, a clinical example of one of these vacuoles. Yeah, Ace.
How are cells able to do this if they can't like see or hear or like feel whatever?
Well,
need to do?
they kind of do. Obviously, they have eyes, ears, but remember we have the glycocalyx, which is the sugar protein that allows recognition. That is the cellular recognition. And so that's how they are able to determine what is stranger danger and what is supposed to be here. But it's when our immune system goes into overdrive frenzy, that suddenly now we have blinders on and we just kill everybody. That's a big problem. But ultimately it is that sugar protein, the glycocalyx, that allows for, remember, the contact and the chemical signaling, allowing for cellular identification. So essentially they are able to see and feel-ish.
So malaria can get through that sugar.
Absolutely. There are quite a few things that can get through that. We're not a perfect being. We're pretty close, but
I don't know about you.
anatomically we are not perfect beings. All right, so in our next chapter, we're going to be discussing, I'm going to say a word that is going to send some of you into the fetal position, PTSD, mitosis. Mitosis. Don't you even shake your head at me. No, we're going to go through mitosis. We're going to talk about here's some words that you've heard before. The anaphase, telophase, metaphase, prophase. Actually, did those backwards. All the phases. Well, what mitosis is if I have one cell and I need more cells, I need to replicate this cell. And what mitosis does is it makes an exact copy. It copies the DNA. It replicates all of the organelles. It grows the lipid bilayer and then pinches them off so we have two identical cells. Identical in every way, right down to the DNA. Mitosis. Well, one of the things that we have to have inside this cell is a way to pull them apart. So we have these things called centrioles. They almost look like, I think, in all of the pictures, they look like little licorice bites. You know, the tiny Twizzlers, they almost look like that. So what happens is this cell is now bippity boppity boo. I am ready to enter the final phase of mitosis. The centrioles will come around and they shoot out these little fibers, and then they pull a tug of war and pull the cells apart. So these are going to be really visible during the stage of mitosis. It's actually during the accessing telophase is when we start to pull them apart. Metaphase is where we start lining them up. Telophase is where we pull them apart. And it helps to organize it and then split the cell into two.
Did prokaryotes do mitosis? Because they didn't have a nucleus, but I know they had DNA in it. So did they have like prokaryotes?
You know what, that's a great question. And honestly, I'm not sure of the answer. I don't think they went through mitosis because they don't have organelles and they don't have a nuclear envelope. I would be willing to bet that they divided by fission, similar to what we see in the mitochondria. Because the mitochondria does not divide by mitosis. The mitochondria divides by fission, which is just like a worm in half and having two worms. This is where it's much more complex, complicated, where we have to split the DNA in half, reassemble the DNA, replicate the organs, undo and then redo the lipid bilayer, forming two identical cells. Very complex. But there are so many things that can go wrong with this. We talked about this a little just for fascination. If you have something that has gotten into your cell, into your nucleus, and gone, hey, this is pretty great. Sure would be ashamed if someone messed up all this DNA. And just starts rewiring the DNA, starts reassembling the pairs, starts reassembling the DNA, because then what happens when that messed up cell replicates?
It's messed up.
It replicates a perfectly messed up cell. And now I've got two messed up cells that are going to replicate into what? Four messed up cells. And so on, and so on, and so on.
Until you die.
Until you die, yeah. Everything ends with us dying. This lecture today has gotten very depressing and very violent. Finally, we've got the brain of the cell, although technically it's not a thinking brain like ours. This is just where all of the instructions for everything the cell could possibly ever need to know. This is the nucleus. Not all cells will contain a nucleus. Only our complex cells that do have organelles and protein-making capabilities are going to have a nucleus. Only cells that have complex capabilities plus possibly protein-making capabilities will have a nucleus. Not all cells do. For example, erythrocytes. Tell me what kind of cell is an erythrocyte? A red blood cell. I talked a little bit yesterday about how red blood cells are kind of a stupid cell. Not that they don't know what they're doing, but if their job is simply to transport, I think of them like 18-wheeler tanker trucks. That's all they do. They take a load, they deliver the load. They pick up a load, they deliver the load, back and forth and back and forth. If I had a nucleus in the cell, it would take up a lot of space. Suddenly now I can't haul the same amount of stuff. Think of like an 18-wheeler tanker truck. And we pick up a shipment in Texas and we drive it to California. We drop it off, turn and burn, pick up a shipment, bring it back to Texas. But now imagine if half of my back cargo area is full of other things and I can't pick up the same volume of shipment. That wouldn't work. So that's why red blood cells don't need a nucleus, because what they do is just repetition. They're programmed to do one thing and one thing only. It's when we get into our more complex cells that have multiple jobs that we start seeing a nucleus and a DNA. So some cells are anucleated, as I got a little ahead of myself, like our erythrocytes. So an advantage is it's not going to take up space, but a disadvantage is it's limited in what it can do. It can't do a whole lot of complex stuff. It doesn't have the instruction manual. I'll give you guys a minute. Here, I'm furious at writing. Comments, questions, concerns so far? Is everybody okay? I love organelles. They're a little bit more common sense to me, because I can relate them a little easier than stupid ionic and covalent bonds.
So since the Golgi apparatus is located close to the nucleus, it doesn't need to have the nucleus because it just shifts, right?
Right. Well, so the nucleus is governing the kingdom of the cell. The Golgi just happens to be one component, one player in the kingdom of the cell. And so it's not like every organelle needs its own nucleus. They're all governed by this single nucleus. Now, we do have some cells that are very, very, very large, in which case we would have multiple nuclei governing a small area of a single cell. For example, some of your nerve cells, some of your muscle cells are multinucleated, meaning that the cell is too big to govern by just one.
So you can have two nucleuses in one cell?
Sure. Okay, so let me refer it. Do you know the show Game of Thrones? Have you heard of this show? Okay, so you had like the whole world of Game of Thrones, But then you had what? You had a ruler over here, you had a ruler over here, you had a ruler over here. Now, unlike Game of Thrones, the rulers in our one world is the cell. Our rulers are not at war with each other. They are working together. But they're communicating so that the cell ultimately works beneficially as a single unit with these different rulers communicating and helping the cell to do its job.
In multinucleated cells, would the multinucleases contain the same information from your?
The same
Absolutely,
DNA.
they're gonna contain the same DNA, they're gonna contain the same information, because it wouldn't be very good if I have a muscle cell. Okay, does this part of the muscle cell need to work differently than this part of the muscle cell? No. I need it to all work exactly the same. So this nucleus is going to tell its cell kingdom to do the exact same thing as this one, exact same thing as this one, so that everybody works together and causes the cell to do its job appropriately. If I've got everybody giving different instructions, that doesn't work.
So Ned Stark just in all of the kingdoms.
So you would have Ned Stark in every single kingdom telling his kingdom exactly the same thing. It's just that the kingdom is too big for a single Ned Stark.
What is an example of like part of our body that has
Muscle cells. Your muscle cells are multinucleated. You have some, not nerve cells. Yeah, probably the most common one I can think of off the top of my dug is a muscle cell. Too big, and too many components, because the way that muscles are bundled together is fascinating. I'm not getting into it right now, but there's too much going on for a single brain. So our nuclear anatomy, we have 4 parts. We have the nuclear envelope, which is just simply the membrane that contains everything. Nucleoplasm, which is just, when I say the word cytoplasm, what am I referring to? The cytoplasm or cytosol, remember that was the jelly-like substance on the inside of the cell. Nucleoplasm is the jelly-like substance on the inside of the nucleus. Yes, yes. We have our chromatin, which is part of our genetic makeup. Chromatin comes together and makes something, what do you think? You have half of these from your mom and half of these from your dad. Chromosomes are made of chromatin. And then finally we have our nucleoli, which is the center of the center.
the brain of the brain.
The brain of the brain, absolutely, the brain of the brain. So those are the 4 components of our nucleus.
What was the third one again?
The third one is our chromatin, which is made up of genetic material. And then this chromatin, it's really pretty cool. We're going to talk about this in chapter 4. It winds, unwinds, and then it comes together in that X. We've all seen the rounded X shape of the chromosome. And then those are what pulls apart, making exact copies for mitosis.
Yeah.
So like you eat human flesh or you inbreeding, is that what's affected the chromatin?
Yeah, so your genetics, but not just on the nucleus level. If you're breeding with your sister or your mom or your dad, whoever, first cousins, that's where your genetic material is too closely related. And so it gives us diversity. You probably look in the mirror and you see components of yourself from your mom and parts of you are from your dad. And then you can see stuff from your grandparents and going back and back and back. The problem is that your genetics are a beautiful tree and we have many, many branches. And when you have offspring, they have a completely different type of tree made up of your branches and their branches. The problem is if your tree looks too much like their tree, you get a stick of a tree and there's no diversity in the branches. And suddenly now your body's like, everything is stranger danger. And that's where you get the genetic abnormalities and you get, because the DNA is so closely related, we get these weird repeats that cause outward clinical signs. We see this a lot in dog breeding, especially if a breed gets successful or popular. The worst one that has ever happened in the history of dogs was Dalmatians. Poor Dalmatians. We wrecked that breed beyond repair. Yeah, well, we wrecked Goldens too. All right, we've got like 4 slides left that we're gonna finish up tomorrow. Because holy smokes, you guys, time flies when we're having fun. Yeah, not all Dalmatians, but what happens when a breed gets popular is that everybody, all the backyard breeders just start breeding, but they don't have any care for, hey, they're like, hey, I got a Dalmatian and you have a Dalmatian. It doesn't really matter if they're brother and sister, right? If it mattered, they wouldn't be able to have babies. No, that's not how it works. And so you get a lot of inbreeding and that causes a lot of genetic abnormalities. But the problem is now, what's going to happen when you replicate the genetic abnormality, even with a non-abnormal dog, you're still going to propose the abnormality.